There we go. Okay, we are now recording. So just to mention and remind everybody, don't forget that test number 3 is this Friday. And as I said in the last class, I believe we're going to do the long problem first this time, and then the multiple choice. And I think I'm going to do one fewer multiple choice to make it a little bit shorter and put one more point onto the written problem, the written work that you send to CrowdMark. So also I wanted to mention that I'm going to do an extra hour of office hours this afternoon. So I'm going to run office hours from 1:30 to 3:30. So that's your chance to come and ask questions about the material that's on the test. Okay, the law problem will have 3 parts. So similar to test 2. So any other questions, quick questions? How much time? Well, you have 40 minutes for the whole thing, so that's really up to you. Okay, I imagine that people will take roughly 25 minutes for the long problem, 15 minutes for the multiple choice, something on that order. Okay, but everybody's different. Okay, but that's about what my thinking is in terms of how much time you should be spending on the different parts. So we're going to switch over to our slideshow now. Yes, we're ending with buoyancy, so static fluids. Okay. So, this comic here is about something called resonance, which is related to oscillations, which is our current topic. So hopefully we will get to it. It's at the very end of the lecture today. If we don't, then we will talk about it next Monday. Okay, but it has to do with what happens when you drive an oscillator at what's called its natural frequency. You can make it oscillate with even larger amplitude. So I wanted to start with, so at the very end of last time, I did the sample problem where there was a mass on a spring, a vertical spring, and somebody picked the mass up and then they dropped it and it started undergoing simple harmonic motion. And I said that in that particular case, that you could use the cosine function to describe its position as a function of time. And so I wanted to show you why that is exactly and talk about what happens when that's not your starting condition. Okay, so the idea is that basically what's happening here is your position will be equal to the amplitude at time equals 0 in this case, and the object was starting at rest, so that means it's at the peak of its motion, okay, where x is equal to the maximum it can be in the positive direction, okay, because that's what they told us happened is someone picked it up and it was at rest and they dropped it. All right, so it's not going to go any higher than that later on. And so if you think about what's happening there and you try and draw a graph of position versus time, x versus time, for your mass, you can see it starts at x equals a at that maximum positive x, okay, and then once you let it go, it starts decreasing in x, goes through the 0 point, goes down to minus a, and then comes back again. And so a cosine is the curve that describes that position as a function of time. Okay, so that's why I said it was okay to use the x equals a cos omega t and then the corresponding velocity and acceleration as a function of time equations that we derived last time using our reference circle. And if we look at our reference circle again, so this is for a horizontal spring, this would be the same kind of starting condition where the spring starts at rest but stretched. Okay, and that corresponds to starting for your reference circle, starting with like your little ball that matches the motion of the mass on the spring on the x-axis. So you're starting at x equals a at time equals 0, which corresponds to theta equals 0 at time equals 0. Okay, you're starting on that horizontal line. So now the question is, what if we don't start at x equals a? So what if the motion starts somewhere else? What if we start at x equals minus a? Or what if we start where the mass is at x equals 0, but it's moving? Okay, then you have to make an adjustment to your position versus time, velocity versus time, acceleration versus time functions. And what you have to do is you have to add what's called a phase angle. Okay, so what that looks like for the cosine function is that you, instead of having x equals a cos omega t, you have x equals a cos omega t plus phi, where phi is your phase angle. And the phi is going to tell you where you're starting on the reference circle. So here's an example with a positive phi. And the idea is instead of starting with the ball right on the x-axis, okay, the ball has rotated up now to a point where x is less than a. X is equal to a cosine of that phase angle. So that's where you're starting. That's your starting point. Okay, but then remember, for this reference circle, you're always moving counterclockwise. So it's going to start at that reference point, and then it's going to, so at some x less than a, and then x will decrease to 0 as you get vertical, and then x will decrease and start increasing in the negative, basically becoming more negative. Okay, so basically, when you're adding a phase angle, you're describing where in the motion you're starting. So what, in other words, what is happening at time equals 0. All right. And so just to draw what that looks like in terms of the function. So again, here's our same situation where we're starting at some angle phi at time equals 0. And what would that look like? So essentially what happens, we have a positive phase angle like this. It's effectively like you took that vertical x-axis, okay, here, on your x versus t, your position versus time graph, and you moved it over, okay? You moved it to the right, okay, by a phase phi, okay? So effectively, you start, and remember, a full cycle for a sine or a cosine in terms of radians, in terms of phi, would be 2 pi. Okay, and so here you're moving something a little bit less than pi over 2 forwards, okay? So you're shifting forwards. So you're starting now, so you can see here, if you look at the vertical axis, you're starting with an x that's less than a, and then it continues to decrease. Okay, so at time equals 0, it's slightly less than a, or about halfway there, and then it decreases to 0, and then it goes negative, which is exactly what we see for our reference circle. Okay, so if phi is positive, it's effectively moving that vertical axis forwards on the function. So you can see it moved forwards on the cosine function. But if phi starts at negative, like this, okay, so if we start below the horizontal on the reference circle, okay, we're starting essentially earlier in the cosine function. And so now it's going to look something like this. You've shoved your vertical axis backwards. So now you're at a point, you're still at a point where x is somewhere between 0 and a, and it's positive. But now as time goes on, your x is getting bigger first before it starts getting smaller again. And so you can see that the shape of that function, okay, matches what you expect for that ball moving counterclockwise about that circle. Okay, I know this is somewhat confusing, so it takes a while to get used to this idea of phase. Yes, so if the phase angle is 0, that means that you've got a cos omega t. So you're starting at that x equals positive a point. Okay. So why don't we try a question on this to see if you can get the hang of it. Like I said, phase angle is a bit confusing, but the reason I want to go over it is our next topic after oscillations is waves, and it's also important when we talk about waves, okay? Because not everything starts at x equals a at time equals 0, and the equivalent thing doesn't always happen for a wave. So I thought we would try a question. So let me set this poll up. So we've got 4 choices here. Okay, so we'll start that going. So the question is, so now I've got position versus time graph for an oscillator here. Okay, x versus t. And the question is, what is the phase angle phi in radians? Okay, remember our phase angles will always be in radians here. Okay, pretty much everything inside that parentheses will be in radians. So what's the phase angle phi for the motion in the position versus time graph shown below? Okay, so what would you have to plug in there for phi to represent this curve? And you can kind of, one hint I can give you here, and you can already see this, right, is that essentially instead of having a cosine curve, we have a sine curve. So think about what happened to that vertical x-axis. Which way did it move, and how much did it move? Because which way it moves will tell you whether phi is positive or negative, and how much it moved will tell you how big phi is. Yeah, you would also add phi, exactly. So you add, so all three of your equations, x versus t, v versus t, acceleration versus time, they would all have the same phase for a given motion. So all of them would be omega t plus whatever the phi is. Okay, I think we're going to do about 10 more seconds here. So if you're not sure, go ahead and guess. You'll find out in a minute. If you don't remember which way it shifts, take a guess. Yeah, omega is angular frequency here. Okay, 5, 4, 3, 2, 1. All right, so we have another dead heat here, almost a tie between A and B. Okay, so it's a toss-up between, is it pi over 2 or is it minus pi over 2? And then if we have a few votes for pi and a couple of votes for minus pi. So let's get rid of that and let's see how you would figure this one out. Okay, so how would you figure this one out? So the first thing to notice is that we moved the vertical axis, that x-axis, backwards here along the cosine function. So if we move backwards, does that mean positive or negative phase angle? What do you guys think? Anyone want to tell me? What does that mean if you move backwards? It means negative. Good. Yes. So this one had to be negative. Okay, so that rules out two of our answers. Okay, I can go back and show you that real quick. See, when you move backwards on the cosine function, that corresponds to a negative phase angle. Okay, so we moved negative, and then the question is, how much did we move negative? Is it pi over 2 or minus pi over 2? Which one did we move? And so then the next thing you just have to remember is that a quarter of a cycle is basically means that your phase angle is 2 pi divided by 4. And so that means that the size of the phase angle is pi over 2, but we move backwards. So the answer is minus pi over 2. All right. So this is an example. So if your oscillator starts at x equals 0 and then rises, because maybe it started on basically you had it in equilibrium, but you had given it somehow some velocity in the positive direction, then your position as a function of time would be a cos omega t minus pi over 2. Okay, that's what your function would look like. And if you go look at what cosine of omega t minus pi over 2 looks like, that is, in fact, a sine function. So all that stuff you did in math class, playing around with trig functions and what happens when you shift trig functions, when you look at cosine of a minus b, for example, that's actually really useful in physics when you're doing these things. I'm not sure what you mean by the distance from x equals 0 is counted backwards. You're essentially going back on your reference circle, okay, by an angle of pi over 2 or 90 degrees. So you're starting at the bottom of your reference circle and then going up. So we shifted the axis on the function pi over 2. Right, so the whole function effectively shifted pi over 2 to the right. That's right, yes, that's another way to think about it. Yeah. Yeah, the dotted line was the original axis. Exactly. So if we look at it, if we go back and look at what I drew before, right, the dotted line was our original axis, okay, and if the phase angle is positive, then the axis moves to the right, and if the phase angle is negative, then the axis moves to the left. Okay, and in this case, the axis moved pi over 2 to the left. Omega t is angular frequency times time. Okay, so that's how shows you how the motion changes with time. Okay, so now we're going to move on from this and talk about another type of oscillator, okay, which is a simple pendulum. So what's a simple pendulum? It's essentially a small object on a massless stick or string of some kind of length L, okay, and now in this case, what happens is a pendulum will undergo simple harmonic motion if your swing angle theta, that angle from the vertical, is small. Okay, and in this case, when you analyze the system, which they did in the pre-lecture, so I'm not going to do it again, what you discover is now what we're looking at is simple harmonic motion in the angular displacement. So with a mass on a spring, it was simple harmonic motion in position x. Right, so we were looking at position displacement, and now we're looking at angular displacement, and we get that the angular acceleration is minus a constant. In this case, it's the acceleration of gravity divided by the length of the pendulum times the angular displacement. And anytime you have acceleration equals minus a constant times displacement, then that will give you simple harmonic motion. Okay, now the reason it's theta here is because we've actually applied something called the small angle approximation, which is incredibly useful in physics and other places. It'll pop up again from time to time that the small angle approximation says that in radians, the sine of theta is approximately theta for angles less than about 15 degrees. Okay, but it's important to remember this is only in radians that it works. Okay, but if we apply the small angle approximation, that's how we end up with a theta on the right of our equation there. And then we can do all the analysis with reference circles we did before and show that this is equal to minus the angular frequency omega squared times the angular displacement theta. Okay. Yes, if the angle was over 15 degrees, you would want to use sine theta. You can analyze that, and in a more advanced mechanics class, people do that. Okay, but we will not do it in this class. And then you can show that, well, it's easy to see, in fact, that angular frequency, which is 2 pi times the regular frequency, which is the number of cycles per second, okay, is just the square root of the acceleration due to gravity divided by the length of the pendulum. Okay, now 2 things really important to notice here. One is that this is not the angular velocity of the pendulum itself. Okay, if you think of the bob on the pendulum as moving in an arc or part of a circular path about the axis, and you look at the angular velocity as a function of time here, okay, it's going to change, right? It's going to be at rest at the 2 max points. It's going to be moving fastest through the middle, okay? So the angular velocity in radians per second of that bob, if you treat it like an object moving in a circle, okay, will vary with time. So that's different than the angular frequency, which is a constant for the motion and is equal to the square root of g over L. So that's one thing to keep in mind. The other thing to notice is that the angular frequency doesn't depend on the mass of the bob. Okay, it doesn't matter what the mass is. The only thing it depends on is what's the acceleration due to gravity where you're located and what's the length of your pendulum. Those are the things that matter. So, and then the period, right, which you can find from 1 over the frequency, is 2 pi the square root of L over G. So I thought we would play around with one of the FETs here so that we can see what this looks like. So I'm going to play around a little bit with the FET. So let's share this. This one is called Pendulum Lab. And hopefully you guys can see that now. Yes, you can see it. Good. Okay, so here's our pendulum. And you can move it up to some angle, say up to 15 degrees, and let it swing. And you can see that right now it has a length of 0.7 meters. Okay, and then you can do things like time the period. So this is the period timer, which tells me the time it takes for one complete cycle, which is back and forth and back again. All right, and it draws it out. So that was about 1.6856 seconds. Okay, and then I can stop it. And now I can change my length. So now if I increase the length, see, I'm going to go all the way up to 1 meter. What's going to happen to the period if I increase the length? Anyone know? What's going to happen if I increase the length? What happens to the period if I increase the length? It should increase. Let's see if it does. So now we're going to give it a try again. Go back up to 15 degrees, and we're going to measure our period. 1, 2, 3. And yes, in fact, it's longer, as we expected. So more length, longer period. Okay, so that's one thing you can do here. You can also, you can prove to yourself that the mass doesn't matter. You can increase the mass and try it again. And you can see you get the exact same period, a little bit more than 2 seconds for a bigger mass. Okay, so that's true. You can also play around with, you can show that even if the angle is smaller, say I start at 5 degrees instead of 15 degrees, and I figure out the period, didn't matter. It's roughly the same. Okay, it should be exactly the same in an ideal world. Okay, I was getting 15 degrees is getting to the point where the approximation for sine theta equals theta isn't as good. So it's a little bit slightly different. Because it does get worse and worse as you get to bigger and bigger angles. So the period varies ever so slightly. That one's very close to the last one. All right, so you can see then you can also, if you want to, turn on the velocity and acceleration and watch the acceleration of our pendulum bob change, you can see that acceleration is always pointing towards equilibrium, which is what you expect, right, for something that undergoes simple harmonic motion, that it's always accelerating back to the equilibrium position. Okay? So anyway, if you have questions, you can go play around with this. All right, and I might come back later and play around with the energy graph if we have time. But for now, I'm going to stop that and go back to my slides. Okay, so we have another poll question to try about pendulums. So let's get a poll going. We got 4 choices again. Okay, so you may or may not know that because a pendulum's period depends on its length like that and doesn't depend on the mass, they make good timing devices. Galileo used pendulums as timing devices because you can figure it basically you always get the same timing for the same length, roughly, for a simple pendulum. So people use them in grandfather clocks and other types of clocks. So this question is about a grandfather clock. And it says, a grandfather clock has a weight at the bottom of a pendulum that can be moved up or down to adjust the timing. So you're essentially adjusting the length by moving the mass up or down. And the question is, if the clock is running slow, if the frequency is too low, what should you do to adjust the time properly? Should you move the weight up, move the weight down, increase the mass, okay, of the weight, or decrease the mass of the weight? Those are your choices. So it's running slow, okay, so that means it's ticking too slowly. Okay, so the frequency is too small. And this is how they actually used to adjust clocks. Literally, they would come in and adjust the where the weight is, the height of the weight. Okay, I think we're going to do about 10 more seconds here. So go ahead and guess. All right, 5, 4, 3, 2, 1. Let's see what everybody thought. So we have a lot more agreement this time. So we've got what looks like about 76 people. Okay, so a large group are voting for A, that you have to move the weight up to fix this grandfather clock. All right, so is that right? Is that what you need to do? Well, what do we need to do? We need to increase the frequency because the frequency is too low. If you want to increase the frequency, you need to decrease the period. And then to decrease the period, you need to decrease the length. Okay? Because as we can see here, right? Again, that period is equal to 2 pi, the square root of length over g. We're not changing g here, okay? So basically higher frequency, smaller period, shorter length, okay? So that means we want to move the weight up. That effectively makes the length of the pendulum shorter, okay? Changing the mass of the weight will not have any impact on T. Yes, you could have looked at the frequency equation. Of course you could have. They're the same. One's, yeah, exactly. They're the same. One's the inverse of the other. So that would be totally fine. Okay, I didn't actually write down the frequency equation. I wrote down the angular frequency equation. You could have used that one too. Yes, so either way would work. All right. So, but you're essentially decreasing your period either way. Good. All right. So that's a simple pendulum. So the next thing we wanted to look at is something called a physical pendulum. Okay. So a simple pendulum is sort of the ideal pendulum where you have a mass, a small mass, like I said, on a long massless string or rod. Okay, so the sort of ideal situation. But pretty much any object can be a pendulum. You just have to give it an axis, fix it at some point, and cause it to swing. And so one example they did in the pre-lecture was to talk about essentially your knee, your leg, your lower leg, basically oscillating about your knee. You can think of your leg as a physical pendulum, where you have a pivot point. And the things that matter here to figure out what your frequency and period of oscillation would be for your physical pendulum are that you need to know where the center of mass of your object is, in this case the leg, and we're going to use h to represent the distance from the pivot point to the center of mass, and you need to know the moment of inertia of the object about the pivot point. So it's very important, it's about the pivot point, okay? And you need to know the mass, right? So that you know what the weight of the leg is, because that's the force that's causing the torque. Okay, so again, you go through the same analysis you went through for a simple pendulum, and you end up with the angular acceleration now of your swinging leg, say, as being minus the mass times g times that distance h from the pivot point to the center of mass. So it's almost like you had the entire mass, like it's like you're modeling your leg as a point mass at the center of mass in a way, like a simple pendulum with all the mass at the center of mass. And then you have to divide by the moment of inertia at the center of mass, and then that's equal to minus omega squared times theta, your angular displacement. And so using the same analysis we did before, we get that the angular frequency, again, all right, which is 2 pi times the regular frequency, is equal to the square root of the thing on top, mgh, divided by the thing on bottom. Basically, it's the square root of that constant that sits in front of the theta in your differential equation that it describes the motion here. Okay, so, and again, period then is 1 over f. And that's how you pick up the 2 pi here, right? Because you divide out the 2 pi from the omega. And you flip it over, and you get I over mgh. Okay, and so if you know, so one of the interesting things here is if you know what your h is, you know where your center of mass is, you know the mass of the object, and you swing it back and forth and measure the period, you can figure out the moment of inertia of an object. So that's kind of a fun experiment to do, where you can dangle an object from some point, measure the period it takes to swing. We do a lab in Physics 132, if you ever take that, where we don't do a physical pendulum, we do something called a torsion pendulum, where the object twists. But it's a similar kind of relationship, and you can use the period of the twisting to figure out the moment of inertia. And we actually have a mystery object in a black box, and we have students try to figure out what's inside the box. It's kind of a fun lab. So I wanted to do an example. Actually, no, I want to do a poll question first, and then we'll do an example. So we have another poll question. This one only has 3 choices. So we'll start this one going. So now you have to imagine that you're an astronaut and you're walking on the moon. So as we said, you can model walking by treating your legs as physical pendulums and swinging your legs. You can model walking as you just swing a leg, swing a leg, swing a leg. And the question is, how would the period of a person's leg when they're on the moon, where now the acceleration due to gravity is smaller, it's about 1/6 of what it is on Earth, it's 1.6 meters per second squared, how would that period compare to the period observed on Earth? Okay, would it be longer on the moon, shorter on the moon, or would it be the same on the moon as it is on Earth? And it's fine if you have to leave early. You can watch the video if you miss anything. So you just have to think about, how does that period depend on the acceleration due to gravity, basically? Does it depend? And if so, how? Okay, I think we're going to do 10 more seconds here. The other thing to think about is, what does it look like when astronauts walk on the moon? You may have seen movies of them walking on the moon. All right, 5, 4, 3, 2, 1. Let's see what everybody thought. So we have even more agreement than last time. We've got 91 people are going for A, that the period would be longer on the moon. So let's have a look. So how does the period depend on G? It does depend on G. And we wrote it down just now. The period is 2 pi the square root of the moment of inertia divided by mgh. So the period is proportional to 1 over the square root of G. Okay, so a smaller G leads to a longer period. So well done. Okay, or even if you just think about what it looked like with people walking on the moon, okay, with less gravity, I mean, they sort of bounce, and they also, because of less gravity, that swing period for their legs is longer. So it kind of looks like they're moving in slow motion effectively. Okay, so because if they're trying to use gravity to help them move here, there's less gravity there, causing less torque. Okay, so I thought we would try an actual physical pendulum example, and this is right out of the textbook. So we have a thin round disc made of acrylic plastic, and they give you the density of the disc, 1.1 grams per cubic centimeters. They tell you that the diameter is 20 centimeters. They tell you it's 1 centimeter thick. So they give you density, they give you diameter, and they give you thickness, so you can use all that to find mass, right? And then they say very small holes drilled through the disc at a point D equals 8 centimeters from the center. So that's going to be our H right there. And the disc is hung from a hole on a nail and set into simple harmonic motion on the surface of the Earth. Now, the other thing they do give you in the problem, which I didn't tell you, was that they also give you the swing angle, but the swing angle is small, and since the swing angle is small, we don't have to worry about it. We know that since it's small, that this is going to undergo simple harmonic motion. So let's see how you would figure this one out. So I'm going to switch to my document camera. There it is. Okay, so what do we have? We have a disk like that. Here's the center of mass is at the center because it's uniform density, and here's the axis of rotation. And they told us that this distance is 8 centimeters. Okay, and that's going to be our h. So h is 0.080 meters, or 8 centimeters. Okay, and they gave us a density of 1.1 grams per cubic centimeter. They gave us a diameter of 20 centimeters, and they gave us a thickness of 1 centimeter for the disk. So now, like I said, you could go ahead and figure out the mass of the object using those. But let's figure out if we need the mass first, okay? So what do we know? We're trying to figure out the period here. Okay, what's the period? So the formula for period is 2 pi the square root of I over mgh. That's our period formula. All right, so we need to figure out some things. We know what h is and m, and well, we don't know m yet. So we have to figure out h, but let's figure out I. Okay, so what do we know about I for a disk? Well, we know I about the center of mass for a disk. We know that that's 1/2 mr squared, right? But we're not swinging about the center of mass. We're swinging about an axis that's 8 centimeters from the center of mass. So now we have to use our parallel axis theorem. So remember that? Our parallel axis theorem says that I would be I about the center of mass plus mh squared. And notice how h is the same h. It's that distance from the center of mass to the axis about which you're swinging. Okay, so for us, this is 1/2 mr squared plus mh squared. So that's the moment of inertia of our object. So let's plug that in to our period formula. So we're going to have 2 pi the square root of 1/2 mr squared plus mh squared, all divided by mgh. It looks like that. This is slightly out of focus. Let me get this to focus ever so slightly better. Okay, so what do we notice? We're really lucky because the masses all cancel out. That's just the mass of the disk. So we don't have to figure out the mass of this disk. So this problem was a little bit evil because they give you all that information about the disk, including the density, and you don't need it. Okay, the masses. I don't typically do that, but sometimes textbook authors like to give you extra information. Like they also gave you the angle that you didn't need. Okay, because in reality, all you need are the dimensions of this object. So now we can actually figure out what our period is. All right, so it's going to be 1/2 the radius, which is half the diameter. So that's going to be 0.10 meters squared, right? Plus the h squared, which is 0.080 meters squared. Extend my square root sign there. And then we have acceleration due to gravity, 9.81 meters per second squared, times our h, which is 0.080 meters. Okay, and notice that you're going to have meters squared on top, meters squared on bottom. Those are going to cancel. You're going to end up with just seconds squared under the square root, which is good because we're trying to solve for time, so it better come out like that. Okay, and then let's just slide down so we have room to write the answer. If you crank that through, you get a period of about 0.76 seconds. So you can see it didn't depend on the mass of the object, right? And we saw that for a simple pendulum, right? That the period doesn't depend on the mass. So it makes sense in this case also that the period doesn't depend on the mass. I'm pretty sure the period formula did include the 2 pi. Let's go back and have a look at it. It should have, unless I made a typo, which is possible. Yep, the period does have a 2 pi in it. Okay. Does in fact have a 2 pi in it. And it also has a 2 pi there. It always has a 2 pi in it for oscillators like this. Okay, so the last thing I wanted to talk about today, so there were a whole bunch of very complicated pre-lecture slides about damped motion and driven motion, and I took them out because we're not going to do anything that complicated in this class. But I did want to talk a little bit about damped motion and driven oscillations and resonance. Okay. So what's damped harmonic motion? So essentially, damped harmonic motion is when you've got friction or air resistance or something else that's causing drag. And what that does is, instead of your object oscillating like a sine or a cosine on and on and on with the same amplitude forever, you start, depending on how much damping, you're going to have a different result. But for very low or slow damping, okay, you'll essentially have something that oscillates, like in graph A there, it oscillates, but the amplitude decreases as you go. And you can kind of see there's also starts to be a slight increase in the period as you go. With even faster damping or stronger, more drag in the system, then the amplitude decreases even faster. Okay, and you can show that the envelope here is actually what's called a decaying exponential. If you know anything about exponentials, I wouldn't worry about that here. And then you get to something we call critical damping, okay, where you start, so in all these cases, we're starting at our max amplitude in the positive direction and then decreasing. And then critical damping, number C here, the oscillating object will just slowly go down to equilibrium without going beyond it. And this is kind of the ideal damping. If you want to stop something from oscillating, you want to critically damp it. Okay, and so this is how they design shock absorbers in cars and things, okay, because otherwise every time you go over a bump, right, your car would oscillate like crazy, right, and you don't want that to happen. You want it to damp out. Or with skyscrapers, when it's windy, can start oscillating, so they often put big dampers in the basements of skyscrapers, and they want to critically damp that oscillation. Okay, over damping, if you damp too much, okay, then it will take a very long time to get to equilibrium, so you'll shift and you won't be able to get back very quickly, and you really want to get back to equilibrium again, and that's why you want to critically damp your motion. So that's the different types of damping, and you can, like I said, you can analyze this mathematically, but we're not going to get into that in this class. And then the last topic I want to talk about is what happens if you drive harmonic motion, so driven harmonic motion. So all of these frequencies we've been talking about so far, so when you start an oscillator moving, what frequency does it oscillate at? We call that the natural frequency, and it's also referred to as the resonant frequency. It's the frequency at which the object resonates, okay, which was the topic of our comic today. And the way this works is, if you have an object, okay, and say it is somewhat damped, and you want to keep it oscillating, you're going to get the largest amplitude oscillations when you drive your oscillator at the resonance frequency. So in other words, you want your force to act at the frequency of the oscillator. And this phenomenon where if you force it at that frequency, then the amplitudes get bigger, this is called resonance. And probably the example that you might be most familiar with is trying to push a little kid, or yourself for that matter, on a swing. Okay, if you want to push a swing and get the biggest swings, you want to push every time it's at its maximum amplitude when it's right in front of you, right? Or if you're pumping it yourself with your legs, then you want to kick at the right time, right? You want to kick when you're at the high point, because you always want to drive it at its natural frequency. Okay, and I wanted to show you one more thing. I know time is up. I'm going to see if I can show you one more thing really quickly here.
In a few seconds of the movie,
I'm going to pause that. let's see if I can show you one more thing. If you have to go, feel free to go. So let me stop that. I want to show you another nice example of resonance. Yeah. So this is a wine glass that somebody is causing to resonate. They're driving it with a given force at the right frequency, and that's what can happen if you drive something at its resonance frequency. You can cause it to shatter. Okay, some people can actually do that with their voice, which I think is kind of spectacular. Okay, I can't actually do that with my voice. All right, so we're going to stop there.